then probability zero event, and you can exclude that from consideration. Yeah. So any 2 points are connected by a unique geodesic. This is fine. And however, later on, maybe what I'll say is something about a place where, yes, even though these are zero measure events, they are things that are worth investigating, but not for pairs of points inside the space. So that should sound a little mystifying, but hopefully we'll demystify it as we go on. Yes. I am starting with a graph which is connected. So therefore, you have paths between pairs of points, and so there is some geodesic, some length path, and therefore you can insert. Don't think of that square bracket. That's just some mathematician's eccentricity. We just want to put all the possible models together in one thing. It's just slickness. I mean, just think of some element of Bourbaki that has influenced me. Hopefully that's the maximum amount of influence that I've had. Okay. All right. Yeah. Okay. So then the distance. I mean, so here's the thing. This is again basically we have used two notations, d sub omega and txy. This is basically because this work was done by a probabilist and a geometer. And for a geometer, the distance is primary, and it depends on this random little omega. Whereas a probabilist thinks of this as a random variable, so this txy is a random variable, and so it's basically what is the primary thing and what it's dependent on is all this is about.
So T is just the sum of all the random variables along gamma. Is that right?
Say that again, Kedar.
T is the sum of the random variables along gamma.
T is the sum of random variables along gamma for gamma which minimizes the distance. So it is the minimum distance.
No, but I thought, okay. So gamma need not minimize? Gamma need not have dw?
Gamma
as a distance?
Not have?
So what is gamma then? It's not the thing that realizes dw.
So here's the point. Say think of Z2. Just forget this probabilistic situation. So think of Z2 with the standard grid, and now you go from 0, 0 to 0, 1. You can go straight, it's length 1, or you can go along the square when it becomes length 3, right? So if you want to take the infimum over all paths connecting 0, 0 to 0, 1, it's going to be 1 because all other paths are of length greater than that. Now we are doing basically a probabilistic version of the same thing. That okay?
So I'm sorry, I didn't understand. So dw is realized by some path, right? By a unique path.
That path is this epsilon guy.
That's what that's what I was calling gamma. Sorry.
Yeah. So epsilon is actually the underlying the geodesic realizing the distance, and T. Oh, I see. Oh, you said gamma, and I see that's this. Okay, good. So
yeah, sorry, I don't know what that symbol is. Sorry.
Yeah, thanks, Kedar. So you've relieved me of some stress that I thought I was completely ignorant and illiterate when I could not differentiate between T and epsilon. So yeah, okay, fine. But yeah, apparently, yeah. So that's it. So epsilon xy is the geometric object which realizes the distance for omega, and T is its length. Is that okay now? Kedar, is that?
Yeah, that's right. Yeah.
Okay, terrific. So now this gadget has been studied widely particularly for Z2, and it continues to be studied for Z2, this and its variants. And yeah, I mean, a lot of work in probability is going on in order to understand some version of CFT.
Z2 means either the link is there or
Z2 is the grid.
Oh,
Z2 is the grid. ZD is basically the grid in n dimensions. Yeah. Yeah. So ignore it because we are not going to talk about it. So yeah. So I'm not going to talk about Z2. For me, it's the single most boring space. I mean, it's something that we do in class 6 and start doing Euclidean geometry. Yeah. Anyway, and this is our point of contention between probabilists and geometers. We regard Z2 as the most boring space. They regard it as the most interesting space. So obviously there's some. Anyway, but I'll tell you what we are interested. So let's go back to this thing. So suppose you have the probability distribution is the silliest probability distribution, which is why they accuse us of saying that we work with the silliest probability distribution, which is Dirac mass, a concentrated R point. However, if you have a Dirac mass supported at 1, then you get the deterministic graph back. Pardon me? Yeah, that's right. Yes.
Is that what you were calling an atom earlier?
Yeah, you can call it an atom. Call it an atom, call it whatever.
But, I mean, you called it something like funny. Is that the atom that you were talking about in the last slide? You said you are excluding atoms last time.
Yeah, that's correct. So we are going to, so for the interesting things, we are going to exclude atoms. I'm just trying to say that, look, this is the setup that geometric group theorists are interested in, is when the background, because they're interested in the geometry of the graph, of the deterministic background. So you can recover it by putting a Dirac mass at 1. And then all the edges become length 1 deterministically. So you recover your background graph. That's all I'm saying.
Just to say, this is called the Dirac delta. That is it.
Fine. I think the point is okay. So is right. Okay, good. So okay, good. Fine. So all right. So now we are going to reinstate put some extra symmetries, and this is where you'll see that we are really not. I mean, this assumption on valence is going to be satisfied and more.
Valence is the number of links coming out.
The number of edges coming out of a vertex. I thought that was borrowed from the chemists.
In solid state physics, we call it coordination number.
So
That's not valence.
Okay. All right. So now suppose we have some extra symmetries. So which means basically you have a group which is given by some finite generating set and some multiplicative law. So then the elements is a discrete object. And this is what we are thinking of as approximating a space. And you have this discrete family of isometries which more or less cover the whole space. Infinite group. Yeah. So for the purposes of this talk, all relevant, I mean, all interesting groups will be infinite. Yeah? So what is the vertex set? But I think there are versions of this which can be done, but I don't think it will be relevant for today's talk. Yeah. So the vertex set of this graph that we consider, S is the generating set. Yeah. So think of, so for example, Z plus Z, Z2. Yeah. And then you look at A is 1, 0, B is 0, 1. And then your S consists of A and B, along with, and we throw in, because we want the graph to be undirected instead of directed, A, B, A inverse, and B inverse. So basically, it's a symmetric generating set. Then with that generating set, the graph that you're going to recover is basically your grid in R2. Okay, so the vertex set consists of the elements of the group, yeah, and edges consists of pairs which differ by a generator. Okay, that's it. Okay, now we want in this deterministic setup, so we want geodesics. So geodesics are just distance minimizing paths in this graph. And now we are going to bring in extra feature of hyperbolicity. This is Gromov-hyperbolicity. It's called, yeah, it's hyperbolic nowadays. Yeah, so I think abelian, when the letter A becomes small, yes. The graph is, so the graph, yeah, so let me just draw this. That's a good idea. So this is 0. Not so. Yeah, so this is 0, A, this is B, this is AB, and this is equal to BA. So that's the thing. This is A, and this is B, and this is B, and this is A. So BA and AB are equal. So that's why you get this square and you can replicate it.
Next point again.
Exactly. That's correct.
So is the setup that the full graph you consider is associated with the symmetry?
So the full graph will have the group as a group of symmetries. It need not be the full group of symmetries. So for example, this one, it has an extra rotation of 90 degrees, which is not recovered by this.
So symmetry, and will the probability distribution respect that symmetry?
No. If it did, it will respect that distribution in law. In terms of the law of the probability distribution. So yeah. Exactly. So
Mahan, if I got rid of the inverses in this example, I'll get a tree. Is that what you're saying?
yes, Kedar?
If I got rid of the inverses in this example,
Yes.
then I'll get a tree.
No. No.
If I just have A, B, and I keep going.
No, you're going to get a directed graph. You're going to get a directed graph.
Without any loops in it, right?
Without, oh, you could.
Unless I have a relation that goes to identity, I will have not.
Directed, guys, right? So AB is still a directed path. BA is also directed.
Yeah.
Kedar, I think it is Manhattan lattice.
I see.
It is
I'm just
something called a
understanding what is the
Manhattan lattice.
connection of loops in the graph and relations in the group. If I come back, if I make a circuit and I come back to some point.
Look, here's the thing. I really don't know Cayley graphs for which this directed thing is of any relevance. So
Okay.
Not
So
talk
you'll always have loops in it and come back.
So so that's a good point. Here's the thing. So suppose your group is, we'll come to this picture in just one slide. Yeah. So just bear with me for a couple of minutes and I'll come. I think it will become one needs pictures for this. Yeah. Okay. No. Those are most boring.
Free group would be...
Yeah, free group would be the right thing. So I'll show you a picture. Yeah. So now let's say what hyperbolicity is. So a geodesic metric space is hyperbolic if all triangles are thin, measured by this delta. So what does that mean? So you have some graph like this, let us say, and then you have a B, and C. And now you have geodesics, which means distance minimizing paths. They might intersect like this. And yeah, my favorite thing, okay, so let's see. So you have this A, B, C. Triangles basically look like this. And then you take a delta neighborhood of 1 that contains the, so the union of the delta neighborhoods of this distance is delta. So think of a delta thick sausage or banana, whatever, around it, yeah, around 2 of these edges. It contains the other guy in its interior. Yeah. Yeah.
What A, B, and C are points at the top?
So you draw. So these wiggly lines are the geodesics in the space.
The A, B, and C are vertices.
A, B, C, B, C are vertices.
And these are geodesics between A to B.
Exactly. So it's a triangle. It's exact.
Deterministic.
Yeah. With this, everything is deterministic. This slide is completely deterministic. Yeah. Okay, so it's basically the collection of points. So if you're non-vegetarian, I'll use sausage.
Yeah, please do.
Okay, good. Yeah. So you'd look at the delta neighborhood basically means all points which are contained within delta in distance of that point of that line.
It's always defined by length of Q.
Yeah, sure. I mean, exactly. Yes.
But now we are in the
Yes.
multiple geodesics.
Sure.
What do you mean by sausage? You mean sausage, union of sausage?
No. I have chosen a triangle. Yeah.
Triangle.
And yeah, so basically you have A, B, and C, and you have some geodesic AB, some geodesic AC, some geodesic BC. So now you have one triangle. Yeah. And then the definition of hyperbolicity says you now take the delta neighborhood of the union of 2 of these guys, 2 of these sides. So that means basically those 2 sausages. The other guy lies in the union of these 2 sausages. Okay? So what is the simplest example? The simplest example is a tree. A, B, and C. You take delta equal to 0. It's the 0 neighborhood of this guy and union this guy. It contains these. Okay. So the hyperbolic plane, HH or HN, these are instances of where you can actually calculate it. It's log 2 or something, yes? That's correct. So this is to be, so a geodesic metric space is delta hyperbolic if any geodesic is contained in, any side is contained in the delta neighborhood of the union of the other two sides for all triangles. Yeah? And this delta has to be uniform. Yeah. Yes. We'll come to that. Very good. For delta equal to 0, these are free groups. As well, yes. That's so absolutely correct. So this is really what Gromov's insight was in the 80s, that there are these completely discrete objects, these groups, which are purely algebraic. And he at some point of time, he just waxes eloquent as far as mathematicians are capable of that. He says, boring and uneventful to geometer psi. Yeah. And then he says, you have to change your viewpoint and try to look at it as if you had bad eyesight. So then these things become blobs which connect up together. And then you really see that it's reflecting the large scale geometry of a continuous hyperbolic space where you can do calculus and where you can do Riemannian geometry. And really these two things are it. So this is really the common structure that's there behind this very discrete setup and a smooth thing where you do all these curvature tensor computations.
You know that the identical delta neighborhood of two guys, what you believe in ABS? No, he wants it for all delta, right?
No. This delta is going to be true. This delta is going to be true for the delta is uniform for a given space. Yeah, so delta is log 2. For Hn, it's log 2. I think so.
Okay, you choose it.
Yeah. Yeah, so it is delta hyperbolic if this is true for all triangles. Yeah. And you say that a group is hyperbolic if the Cayley graph or a Cayley graph is hyperbolic with respect to some finite generating set. Yeah? And the basic point, and this is where I think all these questions about what if it's one geodesic and there is an ambiguity there. And essentially, this basic fact due to Gromov, which starts off this whole thing, says that there is no ambiguity. Yeah. So if it's true for some generating set, it's going to be true for any other generating set with a possibly different delta. So therefore, the hyperbolicity delta depends on the choice of generating set, but hyperbolicity itself does not. So S, yeah. So it is hyperbolic so it is delta hyperbolic for some delta. That's what. So what is something that is not hyperbolic? Let me just finish this up. So the Euclidean plane is not hyperbolic. Now, why? Because you can just take an equilateral triangle and keep scaling it. No side is, there's no uniform delta which will allow you a side to be contained in the union. Yes. Yes. No. So this is the geodesicity is basically about any graph. You take any connected graph, locally finite, as in this case, there will be a distance minimizing path because the valence around a point is finite. Yeah. Oh, because distance between points is, so the lengths of edges are 1. So if 2 points are connected by an edge, the distance between those 2 points is 1. And now you can define, so for any pair of points, you can define the distance by looking at this geodesic length, smallest edge path between those two lengths. So now what does that give you? For any pair of points X and Y, you have a distance defined. So now you can define the distance from a closed subset. This is the infimum of the distance of a point from any subset of that. Right? And so you're looking at. So the only thing is, but this is a physics audience. They should not have this obsession about delta being small. For me, delta is typically a million. Yeah? So.
Do you think the reason why hyperbolic space
Yes.
this idea is the nature of infinity? Because what happens is that like all geodesics.
That's a very profound question. That's a very profound question. Why are you getting scared of asking profound questions?
That question from me.
No, seriously. The next slide will tell you how it connects to the infinity. And the reason why we study these groups is that if you take a bag full of all finitely presented groups, that's a countable thing. Just blindfold, put your hand in and pick one of these guys out. It's going to be hyperbolic. It's going to be either, depending on, there are very precise ways of, there are precise random models for groups, for finitely generated groups. And then, so such groups are ubiquitous. So that's our kind of sales pitch. It's nothing more. Great. Terrific. Good. I'll have to retain these words in my, Shiraz, I'll have to retain these words because this is going to be.
What's happening?
Yeah.
Basically locate. And that finitely goes, nature of geodesics.
Yeah. So yeah. Okay. Yeah. I think I vaguely understand this word, but yeah, maybe. Okay. All right. So now the thing that we want to do is take these two things in the first two slides. There's a percolation, first passage percolation metric. Now you have a background metric which is given by a hyperbolic group. You want to put these two things together. So what is the random geometry of hyperbolic groups? That's what we are asking.
Mahan, before you do that, what's the percolation part of FPP? I didn't understand. You defined this distance problem in the first slide. You get some random distance. Now, what's the percolation aspect?
Oh, the percolation aspect is basically along each edge, water flows. So that's the percolation part. And it flows with a certain probability. And one by that probability is the length of that edge.
Okay, but I'm just asking, usually percolation I think of as asking a yes-no question. Are 2 points connected or not? And in one phase they are, one phase.
So percolation has a bunch of models. What you're talking about, Kedar, is I think this is what Shiraz had also mentioned. This is called Bernoulli percolation, right? So
yeah. But here, is there a yes-no question in FPP?
No. It's a continuous. That's why it's the lengths are distributed. Typically, the interesting models of FPP is when the lengths are distributed continuously between 0 and infinity.
But could I set a time and say up to that time, what fraction of the sample has the water reached, and is there a transition or something like that up to a time?
So that would not really be the correct thing.
Okay, that's all I was asking.
Model. Because it's not going to be about percolation clusters, for instance, which is the issue in Bernoulli percolation.
Yeah, okay. So that's all I was trying to clarify.
Yeah.
Thanks.
So for example, here the correct thing would be, say, if you're back in Z2, which has been studied for a long time, essentially you take you have this metric, right? So this T of XY. So you have a random ball at time N. So for each N, time N, you look at the collection of points that you have, and for every instance of omega, you have the collection of points that you've reached. Yeah,
right.
Sphere. And now what you can do is rescale it. So now you by some appropriate number n, and now you tend to infinity, and so you have these random balls distributed around the origin. Ask something like, in the limit, does it converge to a deterministic shape?
Okay, I understand. Okay, thanks.
So that would be the analogous question there. And the right way of trying to understand this. And this is called, there are versions in the Euclidean thing they're called shape theorems because of precisely this.
flow case by a limit of this distribution.
Oh, no, not a limit of this. Yeah, well, maybe because yeah, true. So it's basically you put it in that slide where infinity was included. You also include 0, and you throw away all that's interesting. Meaning you throw away the open interval 0, infinity. If it's 0, it's connected. If it's infinity, it's not connected. That's how you can interpret it. So this is but I'm not talking about but I'm not talking about Bernoulli percolation. I'm not going to be talking about. Usually, the thing of interest in this is exactly the other domain where something is distributed, and you really want control over tails at 0 and at infinity. That's. I mean, it really is complementary situation to Bernoulli percolation. Okay, and so now I think this is a response to Sandeep's question. So these are a few examples. So this is a skeleton of a. Well, so sorry. This is a tree. This is a delta 0 hyperbolic space. And this is a hyperbolic plane. And this is tiled by, I think, what is it? I think 2, 3, 7, something like that. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 10, 6. Yeah. So this is pi by 6. This is pi by 2. This is how many? 1, 2, 3, 4, 1, 2, 3, 4. 2 pi by 4. Oh, pi by 2 pi by 8, pi by 4. Yeah. So this is so basically there's a 45-degree angle here. There's a 90-degree angle here, and this is 2 pi by 12. So pi by 6 angle here. So that these are all regular triangles in the hyperbolic plane. Pi by 6, pi by 4, pi by 2, and then you tile the whole thing by these triangles. And so these are instances of triangles. But so the thing, if you look at all these bi-infinite geodesics which are starting off, I mean, the geodesics in this are semicircles which are perpendicular to the boundary. And you can take 3 of these guys which touch at infinity. Yeah. That is going to give you, in some sense, those are called ideal triangles. Those are, in some sense, the largest triangles that are there. Now it becomes a Euclidean exercise, right? You have 3 semicircles touching pairwise at infinity, all of them touching the boundary at right angles. And then there is an incircle, the Euclidean incircle. Take that incircle, measure its radius, do this integration of the hyperbolic metric for that radius. That's your number. And that turns out to be, as far as I remember, log 2. Yeah. Okay. And oh, there's one more thing, is that any triple of points on the boundary are invariant under SL2R. Yeah, I mean, meaning you can take any 3 points to any 3 other points. And the isometry group is SL2R or SO21. Yeah. Euclidean ADS, that much is the limit of, yeah. Okay.
In this case, this can be thought of as some group, right?
This is the 2, 3. This is a discrete group. This is certainly a discrete group. So now you can sort of see this Cayley graph here. What you do is you look at this tiling and you look at its dual. So which means you put a vertex for each of these tiles. When the tiles have an edge in common, join them by an edge.
That's the Cayley graph there?
No, this is something else. These are all whacked from the internet. So no, there's this. Oh, maybe it. No, maybe it is. Maybe it is. Maybe it is. So this guy here. This is a triangle. Is it the dual? I haven't checked. So maybe it is. Maybe it is. Maybe it is.
And
maybe.
in this case, the delta would be not within some number.
It will be some number. So the graph is, so there's this standard. So this is really the meaning of, you take this continuous space, you have this discrete gadget, and then you can take these finite amount of cells and crush them down to points. Yeah. So which means now, because of this basic thing about by Gromov, you really transferred information from a geodesic metric space to another space which approximates it. Yeah. So the delta, the delta that you get is going to approximate the original delta, but by approximate, you don't mean approximate to small orders, because this is, you're doing a fairly drastic thing by taking some bounded sets, uniformly bounded, crushing them down to points, right? So the bound of the diameter of each of these guys is going to feed into your delta, but that's it. So here, that's why in this scheme of thinking, the actual delta is not important. All you care about is whether there is some finite delta which works uniformly.
Will you be working with this particular graph later?
No, sir. Oh.
I didn't understand this question about it's some It looks like the two-fold group.
Yeah, this is the two-fold. Okay, so you take this triangle, yeah. So what is the so the triangle has a pi/2 angle here. Now, if you look at there's a fourfold symmetry about this vertex. That fourfold symmetry is actually an element of SL2R or SO21, which fixes this point of the hyperbolic plane and rotates through pi/2. Yeah. Similarly, this gadget it fixes this point and rotates through 2 pi/12. This guy, oh sorry, this one. So it fixes the origin and it's just the rotation by 2 pi/12. I mean this is one gadget I think I can even write out. I mean, it's cost to.
You take a continuous hyperbolic load.
Yes.
Something.
Yeah, exactly. So you look at the, so you
point of view, the group itself is what you will do, not the portion.
Yeah. So and then there are these three rotations. And now you look at the subgroup of SL2R generated by these three rotations. Yeah. That is going to, just as R2 was styled by this guy. If you say, for example, you put a 90-degree rotations. Yeah. So that will give you a gamma or G. Yeah. Here you're going to get, this is your discrete G. And that discrete G has a Cayley graph, which is this. Yeah, I think you're correct. Thanks for pointing out. I didn't realize that.
And the generators are the reflections.
The generators are, well, both are fine.
No, I mean in this case.
Huh?
In this case. In that Cayley graph, the
Here?
generating set is
Here the generators. In this Cayley graph, the ones are the reflections. That's correct. That's correct. Yeah, I mean, yeah, that's true.
And in the modding out picture, any of the black or any of the white will make.
Exactly. That's the fundamental. Okay. Yeah. So, okay, great, terrific. Yeah. So that's it. That's okay. So here, I think in this picture, it's this 4 sticks range. Is this 4 sticks at identity B inverse, A inverse. That's the fundamental domain. Okay. So now this is the prototypical. So this gadget is one-dimensional. This gadget is prototypical two-dimensional. I mean, the free group is one-dimensional and the hyperbolic plane is two-dimensional. Yeah. Okay. And coming back to Sandeep's question, so as you can see, there is a moral boundary here. Yeah? I mean, you try to, in one way of thinking, if you try to force these guys which want to grow freely, for example, trees, and you force them to sit in this myopic Euclidean universe, they will start shrinking the lengths of their edges and they will develop a boundary there. So the Cantor set here is the boundary of the tree, and the boundary of the hyperbolic plane is the circle. That's what's going on here. Okay.
That was a subgroup of SN2R.
Yes.
But in this case, can one think about that?
The free group. Yeah. So the thing is, if you want to have Lie groups inside which your discrete groups are sitting, you are in a very restricted universe. So, I mean, not that that universe is particularly well understood in dimension greater than 3, but it's very restrictive. I mean, it's better to have a little more elbow room so that we have more examples to try out. Right? Okay. So these are kind of, but addressing, if you want to think of this hyperbolic plane and this graph on which you're doing FBP, you won't be far off. Okay. All right. So first thing is, now we want to put these things together. We take this hyperbolic background, do a random flow, and now we are asking how much of this deterministic geometry of a hyperbolic space is reflected in the random hyperbolic geometry.
Just one purpose.
Yeah.
Go back one.
Yes.
I understood that this modding out procedure modded out some geometrical, meaning the hyperbolic plane.
Yes.
Now, the left-hand side was like the Cayley graph of the group.
Correct.
What is the relation? Now,
Yeah.
you're going to put some lengths on that, and that doesn't seem to have any relationship.
Nothing
with
to
the
do with
metric of that.
That's correct. That's absolutely correct. However, so what is this? What are we trying?
Hyperbolic itself.
Yeah. So
Can you please repeat Siraj's question? I couldn't hear it on Zoom. So I understand your answer.
asking, okay, I am going to take this Cayley graph originally embedded in this hyperbolic plane. Now I'll take it out and get to this left side picture. Then I'm going to assign lengths arbitrarily to these edges sitting inside the hyperbolic plane, right? So I'm going to get a random hyperbolic model of this. This
Right.
question, why should that have any, I mean, why should that reflect or have some hyperbolicity properties?
Right.
So we'll come to that. And the reason is basically that hyperbolicity forces it. Yeah, it does not happen.
Mahan, one more point.
It does not quite happen.
So if I didn't understand how the group generators give rise to the picture you're showing, I can still understand something beyond what you're going to say. I mean, can I just think of the picture and doing FPP on this picture and knowing that the picture is hyperbolic?
Think of the left side graph, which is the on the right side graph, and think of doing FPP there. FPP
okay, good.
tree is very boring because the geodesics in the tree remain geodesics in FPP.
Yeah. The top left, if I think of, that should be good.
Think of the two-dimensional grid on the left side. Perfectly fine.
Okay.
Yeah, more or less all the things that we'll be talking about today. This two-dimensional grid picture with the dual graph picture on the left side really captures most of it.
Okay, thank you. Because I think I understood what you meant by group generating the tree, but I didn't fully understand how the group generated this left-hand side top. But that's okay.
Think of that dual graph. That's good enough. And any of these graphs are kind of I mean, whenever you have information on one of these graphs, you have information on the other. So it's fine. You pick up whichever of these graphs you like and work. Okay, fine. So now, so here's the thing. Now we want to basically say that, okay, how much of the background deterministic geometry is reflected in the random geometry when we start doing all this game of allowing the lengths to fluctuate?
Point I think would be that your probability distribution will respect this isomer. That is to say, I mean, each instantiation will allow different edges to be the same, but what the drawings on the graph or whatever edges related by the isometry will have the same.
No. If that was the case, then so if the edges which were related by isometries had the same length in an instance, then you are really a very, I mean,
Okay, and you're saying anyway, each edge has the same probability.
Exactly.
Then it's strange that the graph will remember the fact that it started from this.
Yes, that's what's surprised. Okay, good. Yeah. No, that's true. But here's the thing. Well, let's we'll try to see how much of the geometry is recovered. Maybe you're hoping for too much, but we'll see what happens. No, it won't. That won't. That will not be the case. That will certainly not be the case. That will certainly not be the case. But there will be certain. So basically, what we are doing is okay. So this step, going from the background continuous hyperbolic space to this graph, it retains this coarse hyperbolicity. Where basically you're really, there's some multiplicative constant, you throw away the advantage of doing calculus locally, but you still have these asymptotic properties at infinity. So basically the boundaries remain more or less the same. So there's a precise sense in which you can have a quasi-conformal map, which means not here, but let's say 2 dimensions where you have a under when you go from the background space to the group and its Cayley graph. So there is that at infinity. And so really there's some information that you get back at infinity. That's too naive, but something like that. Yeah, absolutely. What I mean, in the very next slide, I'll try to say what are the kinds of things that you can say that even after you've randomized, you still get back some of these features of hyperbolic geometry. So the parts that create trouble are the parts that are at 0 at infinity. But those are the places where we have difficulty in the proof. So for example, if the probability distribution is supported in 1 by 10,000, 10,000, yeah, then all your instances are going to be quasi-isometric to the original graph you started off with. Yeah. And therefore, we might as well go back and do our standard hyperbolic geometry, standard meaning this graph setup. And you know that each of the individual lengths, though they are not deterministic, they are up to a uniformly bounded multiplicative factor of 10,000, the same as the original guy. Yeah? So, well, the qualitative features at infinity will remain the same.
The number of points at infinity, fine.
No. So here, this is a Cantor set. This is a circle.
Right.
So
then you could get like very widely fluctuating lengths.
Absolutely. You could. You could.
Yeah.
You could. In principle, you could. That's correct. That's correct. Yeah.
I was wondering whether what he's saying is that all fluctuations have to be normalized. At infinity, it's just like.
No. That's not what it is at all. Okay. That's not what it is at all. No. It's not it's not asymptotic ADS with some where something dies down and it's no, that's not what this is about. It's really you allow fluctuations at infinity. Yeah. Yeah. And yeah. What do you get is yeah. Okay. All right. So now, here's the thing. So what's the key thing about this picture again? Essentially, you look at geodesics rays starting, say, at the origin. Then this circle at infinity parameterizes the directions at the point. This is a key feature of hyperbolic space, which is somehow not quite there in Euclidean and most. I mean, so what do we do in the smooth case? I've been going on for ages and I've just probably gotten halfway through.
So easy.
Chalta hai na? Okay, very good. Because this is a more Russian style seminar and I'm very happy with it. Huh? Okay, fine. Yeah. So, so the thing is, if you want to parameterize directions in the Euclidean plane or on a manifold, you take a point, you take the tangent space at that point, and then you take the unit tangent sphere there. So then the points on that unit tangent sphere parameterize directions. Here we are interested in a graph, and there's just some finitely many directions. So how are you going to get anything out of this locally? So the key point is that in hyperbolic space, these infinitesimal directions, you project them out by basically look at those geodesics and you extend them to infinity. Those geodesics never come and hit each other, unlike in the sphere. So you start at the North Pole, geodesics are going to come and hit each other at the South Pole. Yeah? So, but in hyperbolic space, they never intersect, which means directions that are infinitesimal can be captured at infinity. Now, even when you've thrown away the flesh and you've gone to the bare bones model, so maybe that's a better way of thinking about it. The graph is the bare bones of the hyperbolic plane. So even when you just have the bare bones model, the asymptotic directions survive. Yeah. So how do you do that? So basically, you look at geodesics, rays. Geodesics still make sense. So geodesic rays still make sense. Yeah? And then you say that two guys are the same if they remain within a bounded distance of each other, some bounded distance of each other all the way to infinity. Two geodesic rays starting at a point. So for example, in the tree, it's very simple because all rays land at some unique point in the boundary. Yeah? I mean, you can think of this as coding by 0, 1, 2, 3, and then 0, 1, 2, 3, etc., etc. And then you have a sequence where yeah, maybe let's call it 0, 1, 1, 2, 1 bar, 2 bar, because A and B and A must be in this. You just disallow 1 followed by 1 bar. Then that's going to give you a sequence. That sequence is going to code for you a point at the boundary. Yeah? And that's the coding of the Cantor set, right? I mean, it's basically dyadic. I mean, so take base 3 and look at sequences with zeros and 2s. That's the Cantor set. So you get back this gadget. Here in the hyperbolic plane, you take any of these semicircles, they have a unique landing point on the boundary circle. So So it's basically in the hyperbolic plane, or in a smooth manifold where you can actually do curvature computations and the curvature is less than 0, let's say. Then there's a one-to-one map between the infinitesimal directions and directions at infinity. Yeah? So asymptotic. So in the hyperbolic group, what's important is that this asymptotic directions still remain even when you have thrown away calculus. Yeah? So even when you can't do infinitesimal computations, you can do computations at infinity. And in a precise sense, you recover the calculus at infinity. A lot of calculus can be done at infinity. These are fractal sets typically, but still you can do some amount of.
Let's say central point.
Which, this one?
That one,
Yes.
And I choose a point on the boundary.
Yes.
And I vary that.
Yes.
I look for the geodesic starting from that point going to the center.
Yes.
Now there's an infinite number of such things.
Absolutely.
In some finite region, they're going to have to coalesce.
Absolutely correct. That's correct. That's absolutely correct. That's absolutely correct. That's absolutely correct. Yeah. Why is that the case? Basically, and where?
But number of 84.
Yeah. Yeah.
No, and I'm fixing the bullet point and I'm varying the boundary.
And there's a local reason for that. So it's easy to see from this picture. See, what's happening is that there is around this point there are these 4 things, right? Locally, it's looking exactly like this. And this style, you have A and B and B and A. So if you have even-sided polygons inside your inside one of these dual gadgets, there are 2 ways of going around. And that's the local contribution to. Something survives. Because probabilistic means you can't quite talk about every point there. It's measure 0, so you have to throw away a measure 0. I mean, all measure spaces of any reasonable meaning are isomorphic to 0, 1 closed interval with the usual measure space. So that's why, but it's much easier to think of this because then you have the geometric content.
Take that point and then there are 3 immediate neighbors.
Yes.
And so for some interval on the boundary, the geodesic will pass through this one.
That's correct. That's correct. That's correct. And
angles
yes,
be kind of the same kind of pi by 2, pi by
more or less. That's a correct intuition. And 2 of these guys will have some intersection also. I mean, yeah, because there will be points where you don't quite have the same geodesic going. I mean, so what is possible, and you will have this here, and this is in response to Gautamda's question at the very beginning, that yes, between 2 points, even after randomizing, you've killed mismatches. However, what if you are going from, now you have a random, let's say even in a deterministic setup, you take a point here, take a point at infinity. Nothing to guarantee that going off to infinity, there is just one geodesic ray. You can have 2 geodesic rays which stay at distance 10 from each other and walk with each other all the way to infinity. Then there are geodesics which go off to infinity, but they are asymptotic and start at the same point. So this is something that happens in the group setup, in the course setup, in the graph setup, which does not happen in the smooth setup. So this is something that you have to, so they're coarsely unique, which means they lie in some delta neighborhood of each other, but they need not coincide on the nose. This is something you do lose when you go from the smooth geometry. But that should not be too surprising because you've thrown out local information. So you take this very nice, smooth, constant curvature guy, and inside each of these little tiles here, little triangles, you create a little sphere or spherical bubble. That's at some point where positive curvature is concentrated. And if you have a bubble which is big and fat and you have a little narrow neck, then the easiest way is to go around that neck. And so there will be 2 ways. So local non-uniqueness steps in. So which means really this graph is a placeholder for not just this model, but any, so you pass to the quotient. I mean, this is the kind of drastic thing one is doing. You pass to your quotient manifold, you take that, whatever metric you have there, replace it by any metric you like. Now you lift it all back. You're going to get that same tiling back. So which means really the ambiguity is in terms of all possible Riemannian metrics in the quotient. Yeah? The thing is, whatever be those guys, when you pull it back, the asymptotic geometry is still the same. Okay, fine. So now what? Yes?
Which
Yeah.
dynamically triangular random surfaces.
Yes.
So there, if you there's a criticality of the latest model.
Ah,
When you go to the criticality,
yes.
then the actual sequential
Yes.
operation of the manifold will match.
Ah,
It just-
okay. So I think I see where you're coming from, but this is a different kind of universality. I think what you're talking about is a phase transition in terms of maybe some parameter beta. Yeah, so there's some parameter which allows you, I mean, let me go back to the one physical model which I vaguely understand, namely the Ising. So where if you change the temperature or the inverse temperature, then at some point there is, so for example, one of the things that I think should be true, not seen this, is that at very low temperatures, which means high values of beta, the collection of Gibbs states is very large. And once you start increasing the temperature, which is the Curie thing, right? I mean, those start coalescing. And so there is a phase transition, but for different reasons. Here, I don't think that's, this is a kind of universality that happens basically because you've defined things to happen that way. You're not interested in this constant delta. As I said, okay, fine. If it's 10,000 or 10 million, we don't care. That's the real reason behind this particular universality is that all positive numbers are the same in this setup. So, okay. So now what is, so we were talking about this boundary at infinity. And that survives when you randomize.
Sure, of the darkness of the graph, whatever, in terms of what are edges and
Yeah.
but just that much, but the lengths are
Lengths are complete. So you've retained the topology and destroyed the geometry.
enough.
That's enough for the nature of infinity to survive.
Amazing thing. I don't know, for me, it's
Okay.
So, but what sort of questions and what do you mean by hyperbolicity survival?
No, not hyperbolicity survival. What Sandeep is saying, what is the, what the nature of the boundary? This slide.
Are being asked.
So here is the thing. So what is it that we are saying? So let's look at, and I think this is something to do with what Shiraz was asking, what if the thing fluctuates? This basic slide is supposed to say it does not fluctuate. What is it? So the key feature of this hyperbolic group is this boundary. So now you can use, and this is something I've said already, you can use boundary to parameterize directions. There's a standard measure on this, which is basically you look at balls. Now they are just finitely many points. You put the uniform measure on that. Yeah. And now you look at the weak limit as n tends to infinity. That gives you something called the Patterson-Sullivan measure on the boundary. Oh, take the origin, take all points within distance n of it.
On the boundary, everything is happening on the boundary.
No. This is everything happening in the bulk. Yeah? You look at all points, and then you let n tend to infinity.
But measure new on PG, which will be
Oh, yeah. So what I'm saying is basically, so you look at this graph that you had. Yeah. Take your origin. Yeah. Look at balls of radius n around it. Now you put the uniform measure on that. Uniform measure means put one normalized by the cardinality of points at every point.
So are we now in the random setup or what?
No. This is in the yeah, because this is in the purely determined.
Once you say look at a ball with the radius n, right? Then just a single set.
It's a discrete finite set. Set of vertices.
No, but you said balls. Balls around the point. To the vertex, choose all vertices parameterized by within distance something.
Within distance. So your distance is defined. Yeah. So take all points x such that distance between x and identity is n. Or it doesn't matter whether you take it equal to or less than equal to. Now you look at the cardinality. You put Dirac Yeah, so I can't change to mass. I can't change mass to function because to us it's not a function. It's a measure. So you take Dirac mass, divide it out by the cardinality of the ball. So that's a probability measure on the ball of radius n.
There's probability for what? Probability
It's a probability measure on gamma.
Sorry, yeah.
So
What? Yeah, it's the probability for what?
for nothing. It's just a I mean, I mean, a probability for it's okay. Oh, I see.
So, but before that, you gave that finite example. You said take the origin, count all the points that are within some distance.
You're taking vertices.
And count all the vertices that are within some distance. Distance defined in terms of how many links I need to use to go there with the shortest possible path. Is that right?
So the number of links defines for you a distance.
Distance,
yeah?
yes. So count all vertices within a certain distance of the origin. That's what you said.
Yeah. So now you look at all points within a certain distance. Yes.
Yes.
And you want to assign a mass. Okay, maybe this is a better way of saying you want to assign a mass to each of those points.
Yes.
Yes, it's the probability that points lie in the ball. That's exactly it. That's exactly it. Yeah.
So 1 over the number of these points is the mass you assign to each point. Is that right?
Yeah, that's it.
No, but
That's exactly it. That's exactly it.
No, sorry. What is exactly it?
No,
I
no,
didn't hear that.
so for each n, you have such a probability distribution.
oh, it's like a theta function.
Yeah, it's a Heaviside function. It's a Heaviside function between minus on the
Sorry, what is it? Has your graph been specified?
yeah. Oh, it's because it's a Cayley graph of the hyperbolic group.
It's that picture.
Sorry, your graph is specified and the lengths along each vertex, each edge is specified.
Are 1.
This is a deterministic setup.
So some particular.
They're 1.
Every edge has
but-
length 1.
Length one.
But here, this is something about the ball around the origin. What is this boundary stuff? I didn't understand on your slide.
Yeah, we are not yet there.
Okay.
So it's basically we are looking at Yeah.
But there's no probability. It's some number. The theta function integrates to 1. That's why delta function is a bit like that. Okay.
Yeah.
I mean, you're saying it's a function that clicks yes if it's within the ball and no if it's outside.
Yeah, and when it clicks yes, you're giving it a value 1 over the number of points.
Just 1, we won't have it. You want the integral of the function to be 1.
Yeah, so 1 over the number of points in that ball is what you assign to each point in the ball.
Yeah.
Okay, but now about the boundary.
Yeah, good. So now,
I can hardly hear Kedar for some reason.
yeah, Kedar, I think you're probably not using a headphone or something like that, and your voice is coming.
Oh, sorry. I am using a headphone. It's probably a faulty headphone. Can you hear me now?
Yes, much better, much
Yeah,
better.
I was just saying, I understand that each point in the ball gets a weight equal to 1 over the number of points in the ball. So far, I'm good. But you've not connected it to the boundary yet, right?
Correct.
Yeah.
Now here's the thing. So this is some general nonsense. You basically look at your hyperbolic group, you add on the boundary, you get something which is a compact object, right? And now inside that you have a collection of probability measures. Yeah. Okay. So our mass distributions with total integral 1. Now let n tend to infinity. What has happened is that as n tends to infinity, each point in the interior, the mass is going off to 0. So all the mass has shot off to infinity, and you get a way of measuring things at infinity. Yeah.
I see. Okay.
Yeah. It goes off to infinity because each point is losing mass as n becomes larger.
So just to be very concrete, Mahan, if I took one of your pictures that you had on the slide, and I can only draw a finite picture, so I've drawn a finite but large picture with a very jagged edge. And now I do this business of defining 1 over the number of points for larger and larger balls as the weight until I hit some band around that jagged edge. And that defines what you're saying in some limiting procedure, some weight on the boundary. Is that what you're saying?
So here's the thing, if you want an approximation of this stuff on boundary G, and you want to see it inside, and this is how we have really worked with it. you look at the sphere. Yeah? Instead of the ball, you look at the sphere. Huh? And then of which means basically points at distance exactly equal to n from the identity, and look at
Right.
the uniform distribution on that. That's the discretization of this guy.
Okay. Okay.
And if you want to think
Thank
of
you.
that, that's perfectly fine because really that's how Baxter and Sullivan came up with it.
Okay. Thank you.
That's the correct measure. Think of if you want to work it. Okay, so now we have a measure on the boundary, and it makes sense to say, well, what about almost every, etc. So now you have two different qualitative things. One is almost every with respect to direction, the deterministic direction, which is so the boundary of the circle not only has this arc metric, it also has the right measure. So in the discrete setup, so these two gadgets don't really coincide. Somewhat different, but you still have this information of the back. Yeah, I hope it's not too important. No, that's not the forget that. Thank you so much. But think of this pattern as a measure.
So that's what you define, okay? The one over cardinality.
One of the cardinality people.
So we need to break electric lines. Otherwise, the integral, because either expanding sphere, but increase. Unless it's like every point, intersects.
Yes.
Lower and lower amount of electric flux.
Yes.
Because
Yes. True. As a result, but then in order to get that, so this is really where I was about to say that this is one place where the Euclidean equation breaks down. Because if you allow this, and then if you want to get back a flux, you'll have to rescale that sphere to be of radius 1, which is really, you're going back to, we have to scale things down in order to get a tensor. So here, you're really getting something at infinity, which is a measure. You will not have this in Euclidean space. Why? Because in Euclidean space, the circle divided by the disk inside, that's like 1 by r, right? So very little mass is concentrated on the boundary of the sphere. So really, when you see things, I mean, this is a place where the hyperbolic geometry really helps you as opposed to the Euclidean thing. I mean, see, for instance, you have the z plus z acting on the plane. Yeah? The plane has a circle at infinity, consisting of all directions. You look at the z plus z action on that circle, it preserves every point, which means basically you take a line, you act on it by the z plus z, it remains parallel, the direction is the same. That's very, very, very different from what is happening in hyperbolic space. With respect to the Patterson-Sullivan measure, the action is ergodic. There are no independent directions. And in Euclidean space, every direction. That's really one of the features which of hyperbolic space is very challenging. So if something is well defined, it's going to be well defined automatically or for a full measure.
I'm thinking of your construction of measure as a limit as in this case.
That's correct. That's absolutely correct. That's absolutely correct. And there are approximations which are the uniform measures. Okay, so now we have a measure on this boundary with respect to which we not only have a metric on the boundary of new way of measuring distance to that boundary. We also have a metric.
Sorry, one more really dumb question. In the picture you showed, if I do what you're saying and I look at the boundary, some jagged boundary, which is an approximation to what will happen if I really let everything go to infinity, why doesn't every point on that jagged boundary get equal weight by this procedure?
Each point on that boundary gets an equal weight of 0. It's because it's a continuum, right?
No, I meant in this graph, if I have a finite approximation, I'll get 1 over whatever that number is. Right. But it'll be the same number, no? The same small number throughout on the boundary or not?
Yeah, but this is on the boundary. You're going to get the same mass on the boundary of the n sphere for any n. That is correct.
Okay.
Here you've gone off to infinity. And so the mass is going off to 0 for every point, right?
But then I have to take some group of points to define the non-zero function.
Points is basically the collection of geodesics that go off from the point on the n sphere. So basically, you look at that point, and this is what Shiraz was pointing out. After a point, I mean, there will be a whole bunch of things at infinity which come and coalesce at a single point, then go to the origin. So all the fellows that came and coalesced at that point
Right.
onto that end sphere, and that set at infinity is being given roughly the same mass.
Okay, got it.
Measure is related to the point, the length of the point where all the geodesics coalesce from this point at the origin. Are they related?
So it's basically, you look at that point, you go to a geodesic, go to a point, then you diverge out.
Yeah.
If you go to a point of view and look at it from infinity, then things are going to come and coalesce at that point. Then follow, I mean, lots of chaps coming in, meeting from infinity, meeting at a point, then following a single line to the other.
No, I'm saying let me take some boundary points.
Yes.
And find the measure on that. Just integrate this over that. That is some number.
Yes.
Now, how is that number related to the object, where to the length where all the geodesics from that region come and coalesce? At least I will take
Yes. Yes. So here's the thing.
with a direct relation.
So let me just go back to the picture of the previous thing. So here's the thing. So if you go up to N, then you have the thing of saying equal to 2. Then you have these few trees from there, right? All of them are the same. What you would like to say, ask is what is the mass of this matter? Roughly, it should be something like e power minus 2 times blah blah blah. Or e power minus something, some higher order dimension times the distance at which they guide, which is 2. So this 2 is in general, that's what it has a meaning for the product. So even when you don't have inner products looking, you can recover it. With how long two fellows remain uniform close together, this was like it. This is the point of view from within. From point of view from outside is what we are looking at. Yeah. Look at from some place. Take 2 points. Yeah. Just 2 geodesics towards the other. The place where they come together, this can be made precise. The distance of that point from the other, that's the one. So that average product is kinetic number. And if that input product is large, it means the 2 points are equal. Okay, fine. So now we want to so you can sample from your problem. So now we are going to put these things together. There is factor Sullivan measure which is coming from this new form deterministic distribution. There is also a background distribution because of this. So you have it's an interplay of 2 probability measures which are completely unrelated. Okay. The first thing, how do we recover something about you put the 2 fellows together? So what is second measure? The second measure was uniform distribution will not be limit of mean.
Yes, that was the partition.
That is the partition.
And what was the other one?
The other one is the probability distribution, the various instances.
Yeah.
So one is the parameter, the other is the. So one is the probability, one is the geometry. Okay. So first thing is, well, this first result basically says that if you look at geodesic rays in the random metric, they cannot have the behavior that was done. They can't go off to infinity and start accumulating more than one. So what's the state? So you say that a path starting at the origin has a direction xi. Xi is now a point on the Gromov-hyperbolic. So the canvas is on the surface. Yeah, so the xi is on the surface.
So this is again previously geometry or random geometry?
No, this is a path.
No, I mean it's geometry.
The probability of random geometry, but the point is random geometry is a collection of deterministic geometry parameterized by probability space. Right? So you have to say something about almost every deterministic geometry if you want to make a statement about the random. And that's what it is. So you take a path, sigma, you start off at the origin. You say that it has direction A, the only accumulation point of this path at infinity, which means basically it does not have this worrisome problem that was found. So you take a path, and if it starts oscillating near this circular infinity, has an arc of theta with 1 0, then it's going to accumulate on a whole arc. Think of a straight line and then start beginning more. But I thought path will be determined if you give me 2 points. A path is just a map from here by a path of this in a continuous line from 0 to the 0. Here, because we are talking about geometry, we will not have circular. That's it.
No, but can I just say, can I just think of this as the definition of the direction psi given by point at infinity, which is psi? Or is it known as
Sign is deterministic, right? And now you have a path. You have a path in your space, which could move all over there. We say that that path has asymptotic direction sign. If the only point it accumulates to is, there is no R. There is no R. There is no more than 1 point around.
This R means because we are changing the metric.
Yes.
Therefore, it could have. And you are saying, and your point is, it does not in fact fluctuate.
Yes, it does not fluctuate
Asymptotically.
locally. All kinds of things could happen.
And is that follows automatically from the technology, or how does that? I mean, it just comes out. It comes out.
It's a fact.
It's
It's a
fact.
fact.
Okay,
It's the first fact which allows us to take this thing off. Yes.
Okay.
Without
this established.
Without this, it's not.
No, I mean, you showed it.
No, it's not. I mean, it's not. Yeah, it's what it's. It's basically. It's true. It's true. It's just that I think we need some assumption about who will. So let's say zero. I mean, there are no atoms.
But this is the definition, right? Of a path having direction psi.
This is the definition of the path.
Yeah, of a path having direction psi.
Yeah, this is the deterministic.
What is
It's the path. A path has a direction in time.
Yeah.
I've said nothing about any of this.
What is the thing we do?
Yeah.
That you have definition.
Oh, I see.
So the basically says that if you have
So
psi,
that's a random.
this is the random.
Okay.
So this is just a definition of some arbitrary deterministic.
Okay.
What the theorem says is that, well, this is it's not very hard. I mean, what we need is that there are no atoms in the distribution. Oh, I mean, atoms are direct. So no points have mass greater than 0 at the problem. The length. Oh, let's say some. And I know that all of these facts are true for some exponential. Basically, your rho is, I mean, you take some e power minus ax, that integral is finite. Rho is the same. Rho is the probability. Slightly different. Yes, yes. But the thing is, there are 2 ways we can pattern it. One is Gaussian. Basically, Gaussian would be very nice. Keep our mind fresh. So I think even with linear, I mean, for certain, okay, let's assume that the probability distribution is some exponential where I'm completely confident that all of it goes through. Because later on, we will need to use that.
When you define the path with the direction, it can be defined for some determinate geometry geometry.
And this is determined for a deterministic law.
Okay, so now this theorem says somehow different.
The theorem says that, well, you take your probability distribution, assume there is no atoms, that is the part is very good. Okay. Then you look at the random geometry, the geodesics. So omega geodesics, 0 xn omega from 0 to xn, and xn is just some sequence, arbitrary sequence. So in the deterministic background, you take sequences of points converging to that. But that's a notion that makes sense. And now you look at now you take this sequence, you come inside this bulk. Look at random geodesics to these points for an instance of omega, and let n tend to infinity.
So xn like it is one. Sorry, xn is a point.
Oh, xn is a point in the bulk.
The bulk and going further and further away.
It's going further and further away, converging to this specific point on the boundary.
Okay, and O is some point in the bulk which is empty.
O is your origin.
Okay.
And two array, converges to array having direction psi, meaning that's the thing that is defined without the
Having direction right is this. Which there are no other accumulations.
It's the only place in the boundary.
Only place in the boundary and
other.
I mean, this, yeah. Without this, there is no case. And I'm saying it's not a very hard. I mean, it's not hard to put, but if this was not true, then then we would have simply not written not our time.
So geodesics don't spend time on it.
Yeah, they don't. Why is that the case?
And this is true for every assignment of the engineering.
No, I don't. Almost every.
Almost every.
Almost is done in the eye of the beholder.
Yeah, so almost everything measures apart from a measure zero. I mean, all things are measured very only up to measure zero. There's a problem which is that the point is you have to. Otherwise, any subset of a measure zero set is measure zero. Take the Cantor set, middle third Cantor set, standard vector. Any subset of that has measure zero. There's no way of saying anything about it.
Meaning of asymptotically rigid, I mean, asymptotically rigid, asymptotically rigid in this one.
Yeah, in a certain sense, yes. So basically, even if you allow interpolations, even IID translations, the boundary is pin.
Yeah.
Only when something could have moved along the boundary. Is an infinite number of lengths, many times.
Yeah. So what is there in a particular geometric reason why this should happen? Basically, you have
That. Still never. Almost.
the other way.
Sullivan, whatever measures, I mean.
Oh,
It doesn't really come not for this, or not for this, right?
not for this, This is almost every with respect to the probabilities.
Yeah.
So just,
I mean, you have that underlying topology, you got abstracted, and then you have some reasonable probability distribution from this.
I think it's based on the same reason that metrics were done. It's infinite action. This is the infinite problem.
So, sure, let me just, because this is, this would, one would have to work much harder than this. There is a reason.
Also because it grows.
Exactly. So the thing is, if you have bigger, so what does it mean for say something, if you want to occupy 2 points at infinity? It means that you are really doing a path outside an end ball and you are accumulating at 2 different points. Outside an end ball, the deterministic cost you have to pay in hyperbolic space is exponentially increased. Okay. Whereas that's in the Euclidean case, it will only be linear power.
Yeah. And actually, we see this in the very different. The boundary of areas is much more rigid than the boundary of light.
So the self direction is good. And actually the thing is, we can do them that way. Two asymptotic directions, that's right.
But at least the purpose of this here, this geodesic, you're taking a geodesic from here to here, and you want to show that it doesn't propagate on. Now, any finite propagation, finite angle propagation at infinity would be an infinity.
That's correct.
So it would be infinitely suppressed unless the probability distribution was such that
along each of these links, or most of them,
Yes,
it gives you a very small length,
absolutely correct.
which is very suppressed.
That's true. No,
It's the same physics kind of thing.
yeah, but sure, so, that's true.
Yeah.
Those who obey somebody.
Exactly.
So I think here is a, so I think what you made out is a key point. This almost every, this full measure, it depends on the direction. So you can have a full measure set which, so that means the zero measure of instances which you are excluding.
Yeah.
One of which is those things.
Yeah.
That depends on the direction.
Yeah, right.
Right?
Yeah.
So this is, so one cannot expect, and I think that's a key subtle point. This collection of zero measures which you are throwing away. There's one for every direction, but the collection of directions is uncountable. So if you've thrown away all these instances and you want to make the statement uniformly independent of direction, you might be ending up saying something about the empty set or the zero. So you can't, and this problem surfaces somewhere when you want to do things with, it's okay for finitely many points, but you want to say something uniformly. There you really have to impose more restrictions. So I'm pretty sure this holds in greater generality than some extent. So if you want to make statements about all points uniformly, some measure, some observable, some function, etc., then you really have to have more severe stuff. Not even. Okay, fine. I don't know. I mean, no, it was not obvious to us that all is but I think when once we started, yeah,
But some
maybe.
people are not intuitive. You know, because the infinite number of points there.
No.
You have a finite angle.
But I mean, he's allowing the probability for every link to fluctuate.
Every link to fluctuate. So now you've got to go a finite angle and not be killed by a probability. So the only way that will happen is if all of these lengths go very small. Because your geodesic doesn't want to go in infinite.
Finally, you also
Get to that side.
What we want is that the bad approach along the sphere is more efficient than going in.
Yeah, exactly. But that will only happen if length very small. Because otherwise you take a huge length price by your along.
That's right. So it's
That's very
so the thing is, I mean, and this is why I'm not sure this is exactly who Euclidean stuff because it's linearly many versus linearly many guys.
Yeah, I think I mean what's I mean I think internal topological.
Yeah, that's right.
It's not a metric.
No, but it has an infinite number of points.
It has an infinite number of functions.
That's already.
It's the same thing as say for example Euclidean alias boundary sphere.
Yeah, I know, but I mean the thing I'm trying to because there in my mind that comes with also.
But let's
And
forget
I'm
that.
wondering whether all my intuition is governed by that. But no.
I was just thinking you have to go let's say you have to go M units. And not pay a price that is very light.
Yeah.
Okay? Then your probability distribution around each of these links, or at least most of them, has to be so that it's the link is not very small.
Yeah, but
That will keep.
here's the thing. I mean, I don't think this particular intuition will work if it's say something like Euclidean, take theta. You could come back R and go out R. That's still linear. And the boundary thing is pi R. It's just a multiplicative factor. If you really want inefficiency of a larger order.
I agree, at least it will be easier to do.
Yeah.
I certainly it's clearer.
Yeah. I'm not sure. I mean, I don't. So, for example, in the Euclidean setup, which is that the reason is basically they want to define the direction differently. And as far as I know, the full motion of a direction is usually kind of by restating. I'm not sure that even this kind of soft probability is missing.
Yeah.
There are exactly probability models where it's born
Let me the one thing that is true in this Euclidean in 3 plus 1, you won't like time, but in 3 plus 1 dimensions,
Yes, no, this is 3 plus 1. That's not, I love that to call it 3 stages. That's not 3 1. We have a single.
One small question, Mahan. In this claim, this result, it doesn't depend on any properties of that distribution of lengths on each segment.
No. Okay, so
Don't need any bounded variance.
we need no Dirac masses. And I have to look
Variance?
up. It's certainly true for sub-exponential distributions
Okay.
for rho.
You should not allow too much probability here. See.
That's correct. That's exactly the
Right.
kind of thing. So I think this one, if you have, as far as I remember, I have to look up the exact conditions. No mass at 0, concentrated. As far as I remember, that was all. That was all. Yeah. I mean, even at 0, it's okay, provided the mass is less than some critical something or the other.
So I could have an integrable divergence at 0, just no mass at 0.
Yeah, no mass at 0. No mass at 0 is, I think, as far as I remember, that's good enough.
Let me just say one thing that I've always found very interesting about flat space. You know, the Coulomb law
Yeah.
dies out like 1 over r to
Yes,
the power
yes.
3 minus 3.
Correct.
In 4 dimensions, that's just 1 over r, 1 over r.
Period.
Which
Yes.
is the same way as a length at infinity.
Yes.
Scales
True.
like-
True.
And that makes 4-dimensional flat infinity not very rich. In
yes.
5 and higher dimensions, the fact that the Coulomb law in gravity, the Coulomb law scales like 1 by r square, 1 by r cube, where that scales like r, makes
Yes.
infinity quite rich.
I see. I see. That's a very nice thing to do. Yeah. Okay. Great. Here. Yeah. Okay. Fine. So here
No
it's
soft here.
Yeah.
No soft there.
good. Okay. So the first thing is basically says that directions exist. So once you have directions existing, you have a little more. You have basically what is called coalescence. I mean, this is coalescence from inside. That what you were saying was from outside in. Here you have actually coalescence from inside. So two paths starting at 2 points in the bulk, going off. Now you have directions. Yeah. Now you can direct them towards xi. How do they behave? And what this basically says is that, I mean, so two paths would coalesce is if they come together and then they follow some path, one path to infinity. And here's the thing, for almost surely, you start off at two different origins in your bulk, take any direction xi, then the two geodesic, the random geodesics towards xi, they will start off from O1, O2, come together at some point in the bulk, and then they will follow the same path to infinity. Yeah, so basically, if you take the triangle, so to speak, with vertices 1 at infinity xi and vertices at O1, O2, it will look exactly like that tripod. So where A is xi and B and C are xi, O1, O2. Yeah. So this is what's called coalescence. So what does that give you? It basically says that given a point xi, you have a random backward tree. So the collection of all geodesics going towards a point at infinity is now a tree because everything comes together and you don't have loops. Now, loops in the interior would be something, but here would be basically a probability 0 event. You can throw that away. But because of this coalescence, you don't have a forest, you have actually a tree. Yeah? Okay. So now you have this key feature, which is this random backward tree. Given any xi, you look at all geodesics coming in from the bulk. Yeah? Those guys give you a tree in the space. Yeah. So the random backward, so if you fix your point xi at infinity, the random geometry of geodesics towards that is that of a tree. Okay. Not yet. Not yet. So you have to have a little bit of, and this is where a little more work is necessary. But it's, yeah, so there are probability distributions where that happens. So here's the thing. So we say, and this is really addressing Vijay's question. So we say that a backward tree has complete ends if for all other points, you have a point P in this forward direction guy to which it comes and coalesces. Okay.
Start with the direction.
So the previous thing we just said that you look at forward percolation from the bulk. Yeah? But you would like to say that you can really start off all the way from minus infinity, which means any point other than your xi. Yeah? But I mean, you have these trees coming from the bulk. What you want is basically a path that goes all the way to backward infinity, some xi prime. And then when you take the forward guy from there, it comes and coalesces in your 1 xi geodesic. Okay, let me draw a picture. Yeah, let me draw a picture. So you have your hyperbolic plane here, you have your xi here, you have 1 here, and you have this is your forward random geodesic. Now you have points here. What the previous coalescence theorem says is that you have a random backward tree like this. Yeah? What tells you that you can actually have things that go all the way? So suppose this is your xi prime. What tells you that you can have for all these points on the way, there exists a path which goes all the way back to xi prime, so that so that from xi prime to xi you have a random geodesic. You have only stuff. I mean, you could have basically stuff going off and deviating, then having a dead end here. Then going a little forward, you have another dead end. Then somewhere else, something else goes on. So you have a sequence of points converging to xi prime. You don't have a ray converging to xi prime. A priori, it's a possibility. Yeah? And it's a very irritating possibility. Yeah? You would like to say that things really come in from minus infinity, go towards plus infinity. My minus infinity is the xi prime. Yeah. So xi is your plus infinity, xi prime is your minus infinity. Every other point is minus infinity. Yeah. So in order to get around that, so we have this notion. So it has complete ends if this kind of irritating problem does not arise. Yeah, you don't have any geodesic going all the way to xi prime, but you have branching off, and then yeah. So you have a sequence of points converging to xi prime without having a ray, a path going all the way. Yeah, we want to disallow that. I mean, which means basically we want to allow the other thing to. We want to see the other thing because that's the next kind of hurdle. And so now we really want sub-exponential.
The first time is there that there exists P in what in one.
1 xi omega is this forward guy. So this is your P.
P of 1 psi subscript omega.
Oh, it's this random geodesic. 1 xi is a geodesic. Sub omega is according to the probability distribution. And so there's a point P such that the xi prime xi geodesic, it goes here. So basically you can really extend trees all the way backwards. Yeah? And the thing is, so if these edge weights are sub-exponential, then this T xi omega contains a union of bi-infinite geodesics, all of these guys. Yeah? So really bi-infinite now, where xi prime ranges over the entire boundary apart from xi. Yeah? So which means that there will be finite pieces where there will be dead ends, but there will be paths which take you off to all other parts of points at infinity. Oh, this is so, but you can't, suppose you can't extend this backward. This is a dead end. So what is how would one think of it? Take, say, a point there. You have your forward geodesic to xi. Yeah. Around that, now look at a ball there. Yeah. Suppose all the edges there have large length, and you want to go behind that. Then you'll have to backtrack, then go around. It's like this train going to Matharan. I mean, it's really like that. There's a hill which you can't go. Yeah. This is a probabilistic state. It also happens deterministically, but the fact is that these are all uniformly bounded, which you don't really care about. So almost, I mean, the thing is, there will be some dead end is a probability 1 event. And there will be dead ends of arbitrarily large is also a probability 1. You don't know where it will be because you have a huge amount of space available. The entropy of the space is huge. Right? Oh, so now we are taking some the distribution rho, assumption on the distribution. Yeah, that is.
That there do exist in bioinformatics.
No. We are making an assumption on the probability distribution that it's sub-exponential. So that means e power minus ax rho x dx integral is less than infinity. Then you have this theorem. There exists a full measure set such that the backward trees can be extended all the way. See, the earlier thing was with continuous. Yes, now I think it's coming back. You just need continuous with low mass at 0. And then you have, you do have forward direction. Now with sub-exponential, this sub-exponential actually, yeah. So, oh, it's, let me just, yeah. There exists a greater than 0, e power minus ax rho x dx integral 0 to infinity. So it's dominated by some exponentially decaying tail. Okay. All right. So that means stuff can be taken backward. Okay, fine. Now, all right, good. So now I'm really at the point which I wanted your input from. Okay. And there are 2 pictures. So we have 2 minutes for 2 pictures. So what's going on here? So this is so essentially you should think of this whole business as yeah. So really, I mean, this is the correct picture. So you have stuff going off to infinity now. We have excluded that. So there is, for every xi, there is this backward tree. So this is my t xi omega. So for every instance of omega, for every point at the boundary, you have a backward tree. Yeah. Okay. So I have now converted this xi to this north pole here. This is the deterministic setup. So basically, you look at all points from infinity coming in via geodesics. Everything starts becoming exponentially close. This fellow, randomized, gives you this tree picture. Yeah? So here, all the geodesics were remaining distinct, but things were becoming exponentially closer as they're proceeding towards the North Pole. But now you've discretized the set. So now you look at this. This is what's basically what's called a horocycle. So essentially, you look at, I mean, in the deterministic background, there are these round spheres, which are like hyperplanes. I mean, you look at what are these gadgets? These guys are really spheres of infinite radius with center at infinity. Yeah? So basically, you look at the x-axis, look at the point at distance n from the origin, look at the ball of radius n about that point, and look at, so basically you get a large sphere touching the vertical guy tangentially at the origin. Let n tend to infinity. So you get these gadgets. So these are these. So these are called horocycles or horospheres. Okay, but in the discrete setup, now you just have these discretely many points. So what has happened is that now that you have trees, from each of these points, the backward trees are now going to bifurcate. Yeah? So the backward trees from the forward trees from those guys are going to coalesce somewhere. So from each of those points, you can take stuff backwards, and now you're going to hit different patches on the boundary, right? So those patches, because you've covered this whole horocycle, you're going to get some covering of this whole boundary minus xi. So you're going to get these macroscopic sets, one for every point at which on this horocycle. So this is not a continuous gadget, so there's going to be discretely many. There's a z's worth in H2. Okay, that goes back to infinity. That gives you, let us say, it's just a cover, but it's roughly like a partition. Yeah? Which means what? Which means basically there's some collection of covers. Yeah? So for each horocycle like this, you have a cover of the boundary. Yeah? One instance is like this. So for
So you have many different horocycles given the north.
Yes, and that's crucial. So I haven't come to that yet, but I'll get to it now. Suppose you start shrinking this horocycle, which means you take a sphere of inside this, touching the same point xi, but it moves in.
This cover is defined for given choice of the horocycle, right?
So for any horocycle and any instance where you have a full backward tree, take any point and take its backward flow in the random tree, you're going to get a patch, right? Okay, so that means for every So these horocycles are really parameterized by Z, right? I mean, time of flow. And there are two parameters. There's a Z, and then there's this little omega, which is the instance of your random. Yeah? So that's what. So they can be overlapping. They're just a cover, but it's not really problematic to think of them as partitions. Yeah. I mean, they overlap, but not too much in a controlled way. Because you this is something I have not said. You might have two geodesics in the random tree, and this goes back to Gautam's question at the very beginning, right? You are not allowed to hit inside, but asymptotically, two fellows might be agree. See, this is where we pass from backward trees to trees with complete ends, which means basically they've gone all the way. So now you have starting from 2 points, you have two guys which come and coalesce at a certain at one.
Still call that a tree.
No, but it's I mean if you look at its intersection with the interior, it's still a tree, right? There is no equation you're violating. Yeah. In fact, for dimension, I mean, apart from the tree, such points will always exist. It's a measure zeros thing. But for every instance, you will have such a thing. For topological reasons, that's something different. I haven't talked about it, but these guys will exist. So there will be some overlap. How much, we don't. Okay.
This what the concept what I understood the concept of what is it? Horosphere.
Horosphere or horocycle, yes. Oh, okay. So here's the thing. What would be, so instead of touching at the origin, you shift your origin. Take the horosphere passing through 1, 2, 3, 4. So basically, you look at the sphere at centered at n with radius n minus 1. It passes through 1. Let n tend to infinity. So it's going to be basically, so what's happening is on this, look at the vertical line here. So the horosphere is determined by this point at infinity where it's tangent xi, and the point on this line where it intersects. So there's a real line's worth of points where it could intersect, right? So you're basically looking at you can take a round disk, take an x-axis, you demand that your circle touches at +1 and meets this x-axis at right angles at any point along that real line. What point is going to give you a family's worth? Yeah?
Sorry, not too slow, so if I take the upper half plane representation.
Yes. Yes, then it's just the horizontal lines. All the horizontal lines are examples of it. Yeah. So now, that's, I think, key and it's crucial. So now suppose you start moving this point on this vertical guy forward. And then you start taking your backward trees for points in the smaller horocycle. What's happening is that those which were larger sets are going to come together. If you push it backward, they're going to separate out. If you move forward, they're going to come together. So which means what? Which means from this picture of this random backward tree, what you now have is a family of evolving random partitions of the boundary minus xi. Yeah? So the boundary minus xi for every time n, where time n is given by this n where you intersect this vertical line, you have a partition. And so this n now parameterizes the evolution of these partitions. As n moves forward, partitions come together. Partitions or covers come together. Yeah. Fine? Yeah. The partitions become smaller as the horosphere becomes larger. What we would like to think of it is in the other direction. When the horosphere becomes smaller and goes more and more towards infinity, the partitions become coarser. Yeah? More and more of these pieces collect together. Yeah?
Without talking about the horosphere, right? Even if you move 1 point,
how are you
towards the side?
Yes.
Then also the partitions will collapse. Even if you start moving fewer points.
No, but how are you even defining the partitions without a horosphere? It's
So
big.
let's find once for a given horosphere. Now the movement can happen not necessarily by changing the horosphere, but having points on some points in the horosphere move towards.
So you look at all the points on the horosphere moving. If all the points on the horosphere move one step, you have the next horosphere.
Right, but say all the points moving is not necessary. Only a few points move. Then also this some of the partitions will collapse, right?
That is correct. That is correct.
Where that happens.
That's correct. And we want that to happen. Okay. So we want that to happen, to have something uniform. So all right. So you have this collection of partitions coming together. Yeah, you want the whole horosphere to move to have some uniform state. Okay. So now you have these shrinking horospheres. So what you get on the boundary, the trace of this evolution inside on the boundary is a sequence of partitions parameterized by omega, which means you have random partitions, which are evolving with this time n, right? Cover. Coarse partitions. And so once you have this evolution of partitions or well covers, then you can actually measure at every time. If you have this coalescence of partitions, you can have, with respect to this Patterson-Sullivan, something derived from that, you have a loss of information. Basically, you take any compact set, take a point, it is either in some, it's now in, you're going to be saying that it's only in one of these finitely many bigger sets as opposed to smaller sets, yeah? So you can compute a kind of a Shannon entropy or loss of information entropy as you make the partitions coarser. Yeah. Okay. And the theorem, which is, okay, the fact is that the rate of loss of entropy, the precise sense of Shannon entropy, I mean, is exactly equal to the volume entropy of the deterministic space.
Rate with respect to change in n.
Exactly. So the rate, so with n, you have a certain number of partitions coming together. And when partitions come together, there is loss of information. You can compute the rate of loss of information with n, which means basically how much are your pieces becoming larger, right? On an average, that's exactly, so now there is a notion. So this is on the boundary now. Yeah, this is purely on the boundary. You have evolving partitions and you have a rate of loss of entropy, a rate of loss of information, which is what we're calling entropy.
The partition covers a fraction p of the boundary is the entropy p log.
Yeah, this is basically the same thing. Yeah. Here the thing is we have to take this boundary minus xi, so you really want to think of this as R2, and you want to chop it off into some compact piece and look at the loss there. So there's a loss of information that you can compute with these evolving partitions. So that sounds, let's call that lambda. Now you go to your bulk and you look at the volume of balls of radius n. The thing is that lambda, the inner hyperbolic space, that grows like e power lambda n, where e power mu n, where mu is, I mean, it's something like bounded between c e power mu n and 1 by c e power mu n for some fixed mu. That mu is called the volume entropy. This mu, this loss of volume entropy, this volume entropy in the bulk is equal to this loss of information.
Can you say volume entropy?
Volume entropy is basically look at n balls, look at a tree. So then what is it? So it's a regular 4-valent tree. Yeah, it's going to go like what? 4 times 3 power n, right? So it's by e power log 3 whole, I guess, hope that's correct. E power n log 3, right? Yeah. So then the volume entropy is this log 3. So it's basically if your volume grows like e power mu n up to some uniformly bounded multiplicative constants, then that mu is called the volume entropy. Okay.
Rate of growth of the volume.
Rate of growth of the volume. So it's basically take balls, take the cardinality of the ball, take log of that, divide by n, let n tend to infinity, take the limit. Yeah. So that's the volume entropy or topological entropy, whatever of the space. Yeah. What this picture is supposed to say is that the rate of loss of entropy on the boundary by this horoball thing, by this propagation of horospheres, is exactly equal to the volume entropy of the rate, the volume growth of the space. Yes.
Obviously not, but it's not the statement that area and volume are the same things. Oh,
I would not think of that.
Oh,
So this-
no, no,
This
no.
is the random fact. From the random.
I know, I know, but is it a reflection somehow in a mysterious way of that far? I mean, that is to say, the reason I'm asking is that your volume is your volume, right, as you said, and the probability is a statement about the area on the.
That is correct.
So I was wondering, you know.
I mean, I'm sure that feeds in. I'm sure that feeds in. I'm sure that feeds in.
After the average over your problem distribution.
Yeah, okay, no, I
Not,
agree.
not instance by instance.
No, not instance by instance, not instance by.
So policy. Shiraz finds this obvious. But I don't find even that theorem very obvious, so, but I'm just saying, somehow your topology seems powerful enough to encode some.
But it is stated that volume and area will go the same. So will not be true for every. Only be true somehow. Reasonable enough probability grounds.
Yeah.
So I feel that's something the same. I agree.
Yeah, yeah. No, I think there is, yeah, I think the area versus volume, it definitely does happen.
And then what exactly do you mean by the entropy? P log P, right?
Entropy is just P log P.
Not like this. That is, where did this L wait, and sorry, and in the volume part, there was just the rate of the.
Yes, that's correct.
Log of the, basically,
Like that. But in what sense, do you have any sense, why is this an entropy? Why?
Oh,
So you have some, so let me just understand. So you have some boundary.
yeah,
And then there are some patches.
yes. And the
each
patches
patch-
are evolving.
Each patch has some fraction P, right? Yeah, no, but let's, we're not talking about evolution, just fix time.
Yes,
They have some patches.
yes,
And there's some P's. One measure associated with each
That's
of
correct.
them. So there's like a probability P1, P2, sum of them is 1.
yes.
And from that, we will compute P log P, right? From that.
So the thing is, so here the part, here the measure of the boundary minus xi, if you want it to be, you want it to be invariant under the z action. So you don't want the sum of the measures to be exactly equal to 1. It's like basically taking this, you want the circle minus this north pole, you want it to be the real line. So the real line has infinite measure. So you have to look at loss of information in a compact patch of the real line. And you're really asking how many of these pieces come together in a. So given any partition, you can compute its, I mean, given any compact set inside the real line, you have a cover. Let's say, suppose it is a partition by after taking intersections, etc. So you got a partition. Now that gives you a measure, right? So then you can do your Shannon entropy P log P for that particular cover. Yeah.
But why? In having just 1 point removed.
Oh, because then you lose the invariance under the Z, right? You want to see
So if
the
you want to
thing.
make a local state, doesn't matter where.
Yeah. So the thing is, see, here it's basically, it does not really tell you as time goes forward, you're going to have more and more things coming together. You want to say when two fellows from very far away come together, it does not really matter whether you positioned yourself initially, what your initial point is. The origin on the real line should not matter. Yeah.
Suppose
Yeah.
I choose some region of the line.
Yes, yes.
And I call the number of patches, the number
Yes,
of
yes.
that is n, which is a function of.
Yes, correct.
Now, what do I have to do to this n as a function of n to get your entropy?
What do I have to do to the.
There are two things that are equal.
Yes.
One is determined by this n as a function of n, which is just like number of boundary patches as a function
Yes,
of n.
yes.
The second thing was this volume as a function.
Yes, correct.
I just wanted to understand this equation. If you have m as a function of n and v as a function of n,
Yes.
what two things are equal in between?
So it's not quite m as a function of n. Yeah. So it's basically, so suppose,
I could fix.
Sorry, what was the question? I couldn't hear Shiraz.
Shiraz, yeah.
Yeah.
Yeah. So here's the thing. So what Shiraz is asking is, I mean, if you have a number m of these partitions in a fixed patch, what do I have to do in the number m to in terms of this entropy to make it equal to the volume entropy? That's
Yeah, just what the boundary entropy. If I give you m as a function of x, I choose some big enough region of your boundary.
Yeah.
And I give you m as a function of x, number of partitions as a function of your n, this ball.
so here's the thing. I mean,
That doesn't determine.
no, that does not. So because no, yeah. Why? Because say for example, there are two kinds of there is one so there are two kinds of partitions given m. Yeah. One is the best partition is where all they are all, I mean, interior disjoint and have equal mass. The other is one occupies almost everything and the other occupies little pieces. So if the latter one has zero, I mean, it has practically no information, right? And the first has the maximum.
Yes, but on the average in your probability distribution, it will be more like the first and the second.
Ah, so that's the whole thing that one needs to prove. That's the whole thing that one needs to prove, that on the average, you are really getting distributed as in the deterministic case. That's the content of this whole business. That's the content of this whole business.
And then suppose it was going like that.
Then it's fine. Then it's fine. Then it's fine. Yeah. So the content, okay. So now I think I get the question and I think I have a better answer to. Okay. The point of this whole business is that this deterministic setup, okay, so for the deterministic setup, which means you project, say, these little patches, which is this deterministic picture on the right side, yeah, where essentially all these patches have the same area, yeah, which is that gives you the maximum amount of information. Then when things start moving forward, then you have exact numbers. There, it's exactly what Sandeep was saying. It's basically volume equal to area. So where is the content of it's basically once you randomize, essentially up to a fairly strong sense, not just averaging or quenching or annealing, whichever is the correct thing, is that in a fairly strong sense, you get back the deterministic measure from the random. Infinity does not fluctuate very well. Okay, so that's one. And hey, wow.
They're using your Sullivan.
Yes,
right?
yes, true. That's true.
That you're sampling infinity.
That's correct. That's correct.
Astrology plus your measure.
That's true. That is true.
So the idea is putting the topology and this sort of this important idea of infinity. Most things lying at it.
Yes. Yes, that's enough. That's enough is that. Yes. Okay. So this was from inside to the outside. The point is that you can go. Yes.
Is there a sense in which you can talk about this ergosphere or Ergosphere sounds like a horror movie.
So actually, I remember. I think this is terminology I am not guilty about. So it's Thurston's terminology, and I remember as a lowly grad student in my second year, we were attending something where Thurston was sitting in the audience and occasionally getting up and making completely unintelligible comments. And then there was somebody who was talking about horospheres, and he was very British. So somebody from the back said, because these guys are drawn horizontal, right? So he asked, why are they called horospheres? Is it because they are like parallel to the x-axis? So Thurston from behind says, no, very rudely. And then the speaker says, what was the question again? So Thurston from the back says, he's asking if horospheres are called horospheres because they are horizontal. Poor grad student, he was feeling very silly.
This
Yeah.
function, like volume as a function of n and number of
Yes.
patches as a function of n, is it scaled in there in the sense that, is it, as I scale n up,
It's going to be e power mu n.
yeah, so scaling. Fine.
Yeah.
Okay.
Yeah, it's bounded. So the way it happens is that there is some constant c greater than 1, such that c mu power n and 1 by c mu power n
Yeah.
bound the volume
I
of the n
suppose
set.
that I'm asking, you don't say when n is large. It's just always.
It's always true. It's always true. I mean, the only case it's not going to be true is probably a point. So, but even then it's fine because c times 1 mu power 0 and 1 by c power mu power 0. Yeah, I think it's true for globally. Yeah.
Scaling, right?
Yeah.
No, but sir, the boundary doesn't fluctuate kind of increasing sufficient to kind of.
To explain this. Yeah, I was thinking of it, when you can scale it near the boundary and it shows there,
Yeah.
then it works.
No, but fluctuation is not scaling. The fluctuation is just any fluctuation.
No, but if I
The
get-
bulk fluctuates a lot, then the rate might change there.
But if I make n very large, so that everything is happening near the boundary.
No, but n need not be, right?
I know.
So,
But
I can come in the.
I'm not.
Okay, and this is the last picture. It's actually, you can go back is the point. So suppose you have this evolving partitions on the boundary, then you would be able to recover a geometry inside, which is basically something like, so this round stuff, that's the deterministic background. Yeah? So uniform patches filling out your disk, let's say. So there's a way of constructing a graph from there, which is basically taking the dual guy, right? So one vertex for that, and if two touch, you put an edge. We'll do a slight modification because that's going to be helpful. You essentially take two copies of the same thing, yeah? Put vertices only in the second copy and edges from the first copy to the second copy if there's either an intersection, if there's some non-trivial intersection. So there's a reason for this. Why? Because now you want to take a random partition. So what are we trying to do here? We basically have this family of evolving partitions. Now, for given any instance of a random partition, we want to construct one of these horospheres back. Yeah. So that when you look at the thing is partitions, if you have partitions on the boundary or these covers, yeah, coarse partitions, and you have an evolution, yeah, which means basically that has a notion. I mean, that is a precise, one partition comes before another partition if every element of the first is contained in one gadget of the second. Things are becoming quotient. That's so that there is a well ordering which you can actually nail down. So now suppose you're seeing purely on this outside in terms of this family of partitions which are changing. Yeah? You want to construct the bulk from this information. How do, and this is the reconstruction part of the title. What do you do? So for each, so you take a random partition or a random cover, put for each member of that random partition a vertex, and for the deterministic gadget, which is these round things, that's something that you have from the Patterson-Sullivan theory on the boundary. You have this collection of vertices. Now you have your random guy, which is basically, think of this on the left, yeah. From each of those vertices, you put an edge with weight equal to the intersection of this random set with the deterministic set. So you can construct a weighted bipartite graph, one vertex for every element of the random partition, one point for every element of the deterministic background guy, and then you put in edges with weights where the weight reflects how much of the random set intersects your deterministic set. Okay. And then you play something. Basically, what you want is that, so if there is no intersection, that's zero. If there's zero, you want to say that it's actually, it takes infinite time to go there. So you take one by that. This game can be played a little more in a more sophisticated way, how you do this. But then what you have done is you now have from a random partition, you have a coarse metric on the horosphere. And so as the thing evolves, you actually recapture from the sequence of evolving partitions on the boundary. You have a metric in the bulk, which is.
Sorry, as the things evolve, what will happen to the graph?
So what will happen is that so you have your original partition, now you have a lot more, which means many more things in the deterministic will come together. So that's getting reflected. So if you have a rate there, you'll basically say that, okay, this is how much of this rate is going to get reflected back in the bulk. So you should be able to get back at least volume entropy, maybe more. So how much information you put in at the boundary, how much information, I mean, not in the information theoretic sense, how much you actually make your boundary stuff sophisticated is going to be, I mean, how much you decorate it with is going to give you. Okay, great. Yeah.
So now the actual specific form of your probability distribution function.
Yes.
There's very little.
Sub-exponential was crucial. I mean, yeah, sub-exponential was crucial. This can be done. This construction can be done instance by instance. I mean, we want to do it instance by instance and not do some averaging stuff. Because what we want at the end of the day is something like either law of large numbers, central limit theorems. I mean, things more sophisticated than just taking an average and doing an expectation.
Okay, so just coming, I mean, sorry, just coming to connections with physics.
Yeah.
Yeah. We want very particular kinds of measure, right?
Yes.
Very particular, like an Einstein action.
Yes.
Has that entered the scheme at all?
No, so okay, so fine. Let me now you are giving me freedom to speculate, right? Yes?
Yeah.
Good. So here's the thing. I mean, here we have done just just this FPP, which is just metrics there. So on each of these horospheres, what are we doing? We are just constructing a background random metric, nothing else. If you want to put in, say, something else, this is roughly a random Euclidean space, the horospheres. Yeah. So it's something that could be thought of as you're making the patches coarser and coarser. So you're coarse graining at larger and larger scales. Yeah. That's what you're doing. So now you want to decorate the system by something. So here's one simple way one could have a finer model. Take icing on these Euclidean things. Yeah. When you take a coarser partition, you take an average spin on each of these blocks. You have interactions between them, and you allow it to. That's the part which I am familiar. I mean, I am comfortable speculating, and this part I think it can be worked out, and something can be done. And then what is happening is that really what you're getting at the boundary is when you're refining the partitions, right? When you're coming back to the boundary, you're refining the partitions, because making it finer and finer. That's what I think the probabilists call a scaling limit. So basically, we are taking Z2 or ZD, and then so which means basically the hyperbolic geometers favorite and the probabilists favorite geometries are really connected via this rescaling. I mean, where the horospheres are really the Euclidean gadgets, and as you time travel backwards, the mesh is becoming smaller and smaller. So the limiting theory on the boundary minus xi is the scaling limit of the Euclidean things.
But that's more or less from your structure. I mean, you are getting fine.
Yes, that's correct. That's correct. No, I mean, one has to, I mean, I haven't said what happens if you decorate just this background metric with a theory and yeah. So, yeah. So, I mean, this would be probably basically, I think this stuff is, I think the closest in the probability, I mean, it would be the probabilistic formulation of lattice gauge. So the stuff on the horosphere is something like a lattice gauge. There you can actually pass to a scaling limit and the others, assembling all the horospheres together and passing them.
Kind of, it's like the boundary, but somehow
moved inside, yeah.
So
yeah.
From that point of physics, we have this ET bar kind of something that you do to the boundary, which is supposed to be describing the horosphere.
I have no what TT though.
bar deformation. So I was trying to see this kind of graph that you have here.
Yeah.
Where you reconstruct basically this
Yes.
slice, whether that can be related to.
Oh, wow. Great. Excellent. So this is the first time I'm hearing these letters. So you'll have to explain to me what these letters mean. But
Basically, that's what is happening, right? You are at the boundary, and then you are reconstructing a slice of the bulk, which is.
that's correct. That's exactly correct. That's exactly correct. Yeah, yeah. So I spoke to Rajesh at some point of time, and he was saying that this horospherical slicing is not something that is typical in the physics literature. You want to do a spherical slicing where
but it's
everything
same,
in.
because we have this upper half plane model. And
Yeah.
this is like moving the x-axis about, right?
That's correct. So these gadgets, the horospheres are exactly the horizontal guys. Yes, or the horizontal
Like
guys.
single point, got it.
Yeah.
It's like singles out the point at infinity.
Singles out at the point at infinity. That's exactly right. That's exactly right.
Moving boundary inward.
Yeah. Oh, yeah. So, oh, great. Terrific. Because this is, I mean, so the thing is, and this is really what I wanted to ask is, so you have these trees. Now forget that you have this point xi at infinity, whether they're forward trees, backward trees, doesn't really matter. You can actually take patches on the boundary, A and B, and you have these trees that come in and then they go out to the other end. That's something like a random geometry version of a coupling between yeah. So it's a tree version of something like that should be Ryuta something or the other. So I don't know where that's. So what I'm saying is that now we have talked about stuff where everything is going towards a point, yeah. But now you can look at the random geometry model where you isolate a patch A on the boundary, a patch B on the boundary, and you're asking for how much information travels between them. Yeah. Whereas, so the thing is in this bits, what is it, string bits, or what is it called? Yeah, bit threads. Yeah. So yeah, threads. Yeah. So there you just have lines going between them, and they don't come together or separate out, and you're really doing something like a mass flow min cut thing of that, right? In these areas. Here, what you would have is essentially stuff coming together and then separating out again, right? So there'll be just basically trees, but coming in from outside, going out from. What I would really like is how to get information out of coupling between sets of positive measure on the boundary in terms of this. This is I mean, and this is really, I mean, what if my real vested interest in talking to you guys is especially this, if you have something where I could look in the physics literature.
But I don't maybe another path related. Is there a problem? Can you write down that on this thing, some probability measure, the original probability measure,
Yeah.
that we could think of as some sort of specialization of an.
Oh, that's a thought. That would be wonderful. That would be wonderful. So, which basically means, so I think, okay, here is, I guess, the point. So the Einstein action basically, I mean, the differential geometric object is the Ricci curvature, right? Ricci curvature does translate to something here, and it has something very closely associated with volume growth of small balls even a fractal. Let me look up the literature a little bit. But it might actually just be this, might just be the volume growth. I mean, the problem is that there it's really, I mean, the Ricci is really about growth of small balls, right? Yes, yes, yes. Yeah.
Deep inside, it's still close.
Deep, say that again.
Inside.
Yeah.
Far from the boundary, it's very close.
That's correct. That's absolutely correct. That's absolutely correct. Yeah, that's true. That's absolutely true. So the scaling limit as t goes to minus infinity should be the scaling limit. Yeah.
Get more than area is. I mean, that is what you've thrown out.
Yeah.
Well, what is your picture when you are wanting to connect to new technology or flow of information? You have this sequence of towers or particles.
Yes. 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 So okay. So here's the thing. I mean, what is the analog of the flow here? It is this forward direction inside the space. Yes. So what one has to do is essentially replace that one directional flow from all of the rest of the space. So this would really be something like boundary minus xi to xi. That's the partition that we are looking at here. Yes.
How your, let's say you take some region on the boundary for some horosphere.
Yeah.
You change the horosphere. So, okay, your some horosphere, you change your horosphere and your cover, change.
Yeah.
Is there a sense in which that information is restricted to some part of the bulk and not the whole part?
Say that again.
And bulk reconstruction. Yeah, it seems to be the case, right? That only some part of the bulk
Yes.
cares about, you take some part of the boundary
Yeah.
and see how under your, let me call your change of horospheres RG flow.
Yes.
You know,
Yes.
it's-
This is exactly what. Yeah. Okay.
Only some part of the bulk keeps that track of that information about how that the boundary information is sequentially changing. If there is only some part of the bulk,
Yes.
then that's a star. Because then, what RT says is some boundary of that bulk, blah, blah, is.
Now, this sounds very interesting, but I'll have to wrap my head around.
Yeah, I'm not saying it very precisely, but the key is that in RT is really is that you have the full boundary is part of the boundary, and information in that part is connected to some part of the part.
Yes.
And I was just trying to ask.
Okay, so what? So what?
Okay.
Okay, so essentially what you're saying is that suppose you fix a patch on the boundary. Yes. Is that naturally connected to a fixed part of the bulk? That answer is yes.
It's not.
Yeah.
I mean, I know you have the preferred point and you do the backward flow and then you have the xi primes.
No. There's a more direct way of doing that. You look at any pair of points on that patch and join it by the random geodesic. Take the union of all these geodesics. That's the part of the bulk.
And it's a well-defined.
It's definitely a very well defined.
It's star. Okay. So that seems to have some localized region of the product which are associated.
It opens up at infinity to this patch.
This patch, yeah.
Yes.
But
And does not share anything with anything else.
it does not.
So more like a thread that connects
Yes.
one part of the
This is-
boundary to the other part, not the artisan, the thing that intersects optimally with the artisan.
That would be A and B. This is basically A and A. It's if you look at A and A itself. A and A itself.
No, that's okay.
That gives you all the bit threads from A to A. Is yeah.
But okay, I mean, it's a sort of stuff. Yeah, you guys need a big thread story.
So it is just the rigid continuous picture of this. I mean, he's talking about joining all the geodesics. Right?
Yeah.
So the geodesics.
Yeah.
These ones from Xi and Xi to get that joint.
Yeah.
Yeah. So you let xi range over one set, xi prime range over another set, and you look at all the, that's.
Some notion intrinsic to the patch itself.
So the intrinsic to the patch itself would be stuff from itself to itself. So this is already very helpful. Okay, good. Yeah.
Was what was just really meaningful after so much.
And- No, the minimal data is because the minimal data is dictated by how much we actually understand.
When you talk about this reconstruction,
Yes.
we reconstruct the metric on the first.
That's correct. That's correct.
What is the metric to be reconstructed? How is that a priori defined in the first place?
Oh, so for the whole instance, little omega, you're going to have so there's a bulk metric, right? Now you've forgotten the bulk metric and you've recorded it in some partitions. That was the forward part of the story, which is the easy part. Now you don't know what is there, that there is a bulk, you have no idea. You just have this information of evolving partitions. Is there a bulk that you can do? Now you do that bulk construction. Now on that bulk, you have natural horospheres, blah, blah, blah. Reverse the construction, you get back this, get back the information. So basically it's
Exactly. Precisely.
up to uniform bounded multiplicative constants probabilistically. That's how much we can say right now. Okay, terrific. Thank you, guys. No, thank you for